Okay, so we're going to continue our talk with exponential and logistic modeling. We're going to look at a lot more kind of story problem stuff on this, okay? So first of all, it's talking about the population model. We have our basic formula, bear with me here. We have our basic formula, y equals a times b to the x. Well, if we're talking about population, we can talk about kind of that initial value is the initial population. So instead of giving that formula, we can use this new formula where p sub 0 is the initial population. And r is the percentage rate of increase or decrease. So r is as a decimal, right? So instead of a percent, you're going to write that as a decimal. And then the time is usually in years. If it's different, it would tell you how to write that. All right, so this is going to kind of be your go-to formula for this section or any kind of population model. So part of your homework is just talking about, is this exponential growth or exponential decay? We've talked about that already, but remember that growth is going to be if your rate of increase is positive. So again, think about the original formula there. Population equals the initial population times 1 plus r. So think about number 1 here. What would r have to be in that problem? Right? Kind of like 1 plus r equals 1.09. Or maybe you just know that r is going to equal 0.09. So if r is positive, that's going to be growing population. So number 1 here would be growth. And then what is the percentage rate? So remember that r is a percent. So 0.09 would be a 9% growth rate. So looking at number 2, think about what r would have to be on that one. 1 plus r equals 0.005. R is going to have to be negative on this, right? Or if you solve this equation, r is going to be equal to negative 0.95. So since that's a negative r value, or because our base is less than 1, that's going to be a decay function. And that's a 95% decay rate. That population's not doing so well. Real quick, I don't think you need to say negative 95% because you say decay, it's implying that it's negative. The other thing I want you to be able to do is you write the equation given information. So it says the initial value is 5 and it's increasing at 17% a year. So again, our formula is that initial population times 1 plus r. So you're just plugging that in here. So for number 3, our population model would be 5 times 1 plus, remember this is 17%, so that would be 0.17. It's like I'm missing something. Shouldn't that be to the t power? Sorry, look at me going back here. Look, you've been letting me mess that up, huh? This would be to the t power. I kind of was leaving that off. This would be to the t power, So I think a better answer here would be 5 times 1.17 to the t power. All right, so then number 4 here, it's decreasing. I'm going to have you do this one as a question. But remember, because it's decreasing, that means that r is negative, so we're going to be actually subtracting. So notice it doesn't say negative 2.6, but because it says decreasing, it's implied that that would be 0.026 to the t power. Which would be like 0.974, right? So 28,900 times 0.974 to the t power. And again, I know some of the ones yesterday were kind of confusing whether they were growth or decay. With population, it's really easy because if the rate is positive, it's growing. If the rate is negative, it's decaying or decreasing. Then we're something like this. It says the 2000 population of Jacksonville, Florida was 736,000 and was increasing at a rate of 1.49% each year. At that rate, when will the population be 1 million? I think I want to do this one in class because I want to show you how we can use a graphing calculator to do this, but let's at least write the equation and then we'll graph it together to solve this. So again, it's kind of up to you if you want to use the whole big number or like the one that we did yesterday where you can say like in millions. You could do that, but I'll just do the big numbers and then we can talk in class about what you think. So if we're going to write this population model, our initial population is 736,000, and it's increasing at a rate of 1.49%, so that would be 0.0149 to the t power. And we did one like this yesterday where we were just using kind of guess and check to figure this out. But I want to show you how we can use the calculators to actually get an exact answer here. So this would be our model for the Jacksonville, Florida population. At what rate will the population be 1 million? Well, think about, like, we want to know when will the population be 1 million. So I kind of want to know, did I do that right? Yeah. I want to know when will this equal this. So, you know, you could go ahead and graph those and see what they would do. But I'm going to do this with you tomorrow. So I'm going to leave this here. We're going to leave this open, right? And we'll do this one together. Number 6 says, suppose the half-life of a certain radioactive substance is 20 days and there are 5 grams present initially. Find the time when there'll be 1 gram left. Maybe you have some good or bad memories from chemistry and half-life stuff. I'm going to do this one, and then later we will talk more about half-life and do things a different way. But I want to show you one way that you can do half-life stuff. So remember from chemistry that half-life means how long it takes for half the substance to decay. So this one tells us that the half-life is 20 days. So that means in 20 days, there will only be half left. And we know there were 5 grams originally. So 20 days, there's only going to be half left. Or in this case, half of 5 would be, there would be 2.5 grams left. And so you need to figure out, like, how could I write that equation? It's not quite the same as the population model, but we are going to use that, like y equals a times b to the x model. And remember that a represents your initial value. So we know that there's 5 grams left, or I mean at the beginning. So we could say y equals 5 times b to the x power. And what we need to figure out is how to do this. And there's a great example in your book using this. And honestly, that's what I looked at when I was doing this. There's another way we can do half-life, and we'll talk about that later on in the chapter. But for now, because it's half-life, you can make the base equal a half. And then you want to think about what time can we make it, or what would the exponent be so that after 20 days, so when I plug 20 in for x, I want there to be 2.5 grams left. And basically I want to be able to take 5 times 1/2, right? And I want to be able to get 2.5. But I also want to be able for that to apply to everything. And so what works out is every time that you do a problem like this, if you know the initial amount and you know it's a half-life, you can set this equal to x divided by the half-life, which in this case is 20. And that would be the equation that gives you the half-life for that substance. And you can kind of check it. If you plug 20 in there, you're going to get 20 over 20, which is 1. If you plug 1 in there, you're going to get like 1/2 to the 1/20th power, which is really, really small, which means it's not going to change that much. And as you plug in bigger numbers than 20, it's going to lose more than half of it. And so that's kind of a really cool way. And again, I want to know when there'll be 1 gram left. And again, this is the new part that I want to do in class tomorrow. But basically, again, I want to know when will this equal 1. So I want to kind of find where those cross. And we're going to do that together on the calculator so you can practice doing that. So again, we're not going to actually answer this one all the way, but this is where we're going to start in class tomorrow. Okay, so there's actually some on your homework tomorrow that you're going to be doing on the calculators as well. And so I want to make sure that I'm here to help you with the calculator stuff on this part. Okay, so that's all I have for now. And yeah.